What I'd like to talk to you about today is anyons and their experimental manifestations. It's kind of orthogonal to, well, not quite orthogonal, but it's pretty far from everything else we had in this conference so far. I'll list my collaborators as we go along. There will also be large parts of the talk which are just me reviewing works of the, kind of the founding fathers. And have been funded by various sources, Yossi, and ISF Quantum. Now, the talk will cover mostly the issues coming from the field of topological states of matter. And because of that, I decided to divide the talk into two parts, a short advertisement and then the rest. And the advertisement is going to be for a course dealing with topological quantum matter. So if I manage to get you interested in the field and you'd like to hear more, then there's an online course prepared by several of my friends at Weizmann and myself. And it covers basically the subjects which make up this field, the quantum Hall effect, I'll talk a lot about it, topological superconductivity, topological insulators, states of topological order, which will also be important in this context, and various others. And you can find it on YouTube. There are 65 videos, and I highly recommend the course to you and to your students. So now to the rest of the talk. So, quantum mechanics is the subject of this conference, is the subject of occupies large parts of our lives. And I would like to say that it is made of two parts. Actually, I was yesterday, I think Ellie was saying that everything quantum comes from interference. I'd like to say that the first half comes from interference. And this is, the story of the double slit experiment. We are going to look at the interference here. It will look a little bit different. And I'll explain what this setting, how it carries out the interference, the basic idea of quantum interference. And you sum two amplitudes, you weigh them, you square them and take the absolute value, and that's the first thing. But then there's another pillar to quantum mechanics, which is as important as the notion of quantum interference, and less emphasized here. And this is the notion of quantum statistics. And there's a difference between fermions and bosons. And the difference is if you have a many-body wave function with many, many fermions or with many, many bosons, not every wave function that solves the Schrödinger equation is a kosher wave function. Only those which satisfy a certain symmetry property. If you have bosons, the wave function should be symmetric to the interchange of two particles, and if you have fermions, it should be antisymmetric. Now, it's only a minus sign. Should we care? So I think there are quite a few people either from Tel Aviv here or with some Tel Aviv past. So when I was a student, I had a lab TA, not Sandu, someone else. Probably many of you knew him, Yoav Ben Dov, unfortunately he passed away. And at some point, as an answer to a question of mine, he said, minus signs are not important here. This was because I didn't understand some derivation. Now, this is an exception to that. This minus sign is of huge importance. We know it. Fermions, because of that minus sign, satisfy the Pauli principle, which gives rise to the periodic table. And they form metals when they accumulate many of them. and bosons, because of the absence of this minus sign, form superfluids and can flow with no dissipation. So it's a minus sign with a huge importance. But now, are there any other possibilities other than fermions and bosons? For a long time, the dogma was that those are the only possible states. But in fact, now we know that there are many others. And I think it was Frank Wilczek who gave this the nice name, anyons. Anything is possible, and that's what I'd like to talk about. So what do we mean when we talk about anyons? The systems we have in the lab do not have elementary particles which are not fermions, which are neither fermions nor bosons. In fact, you know, in the systems as a condensed matter physicist, I think of mostly the systems are made of electrons. And there are capital N electrons, and they are fermions. And the wave function they satisfy must get a minus sign when you interchange them. But the systems sometimes have collective excitations, which we call quasi-particles, which are emerging degrees of freedom, which in this case are denoted by capital R, and the plot has 4 of them. And the wave function depends on those as parameters. Now, if you change these parameters adiabatically, and if the Hamiltonian is such that there's an energy gap between the ground state and the excited states, then by the adiabatic theorem, if you carry out an interchange of these two parameters, the wave function will come back to itself up to a phase, a Berry phase. Now you can calculate that phase, and in many instances, which are the ones we're going to talk about here, this phase will be quantized and will not depend on the trajectory that the quasi-particles take. Whether they're interchanged this way or that way will not make a difference. What will make a difference, it will have to be adiabatic. But other than that, the phase factor will be fixed. Now, when that phase factor is neither 0 nor pi, then we call the particles anyons, and that goes back to the founding fathers of anionic physics, Linus, Myrheim, and Wilczek. Now, it can even go more than that. You know, what I told you here relied on the fact that there's a single ground state. If you have only a single ground state and you do that, then the adiabatic theorem tells you will get back to the same ground state up to a phase. But if there are more than, if there's a whole bunch of ground states, then by the time you finished a cyclic change of the parameters, you come back to a ground state, but not necessarily to the original ground state. So you don't multiply the ground state by a phase, you multiply it by a unitary transformation, but in a unitary transformation that operates only within the subspace of the ground states.
Andy?
Yes.
Talking here about Berry phases?
Yes. Yes. This comes from my, sorry. It's a Berry phase, yes. And in this case, in this case, it's a non-abelian Berry phase. Exactly. Now, in the cases that we will talk about, the degeneracy of the ground state, in those cases where it occurs, it's not that every anionic system has this degenerate ground state. It's only a subclass called non-abelian states, and I'll explain the name in a minute. In that class of states, the ground state, the degeneracy of the ground state goes exponentially with the number of quasi-particles. Now, of course, by itself, this exponential growth is not that exciting. You know, if each quasi-particle has a spin 1/2, then and there was nothing that breaks spin degeneracy, we would have a 2 to the power n degenerate ground state. But here we're going to talk about the situations where lambda is not an integer number. In fact, in the case I'm going to talk about, it's the square root of 2, which means it's not that each particle has a spin 1/2. It's a collective set of degrees of freedom which are non-local. But we'll get to that. Now, when that happens, then we have this lambda to the power n ground states. We can list them all. These two should have been a lambda, sorry. Each one of them depends on the parameters, which are the positions. And when we interchange two of these positions, we apply a unitary transformation that acts only within this subspace. Now, that unitary transformation is a matrix. And when you apply a sequence of such interchanges, you multiply matrices. Matrix products are not abelian, and therefore the final state depends on the order at which you carried out the interchanges, and this is the source of the name non-abelian. Now it turns out that the final state depends on the order at which you did the interchanges, but again does not depend on the geometry of the interchanges, depends only on the topology. Here, for example, you had 3 quasi-particles, you interchange first 2 and 3, then 3 and 1, then 2 and 1, and so on. And the outcome depends only on the, on this topology. This is known in the jargon as braiding. You can look at this and it looks like doing braiding. Not that I am a big expert in that, but that is how people do braids. Now, this is as robust as an electronic system can get. You go from one state to another, and no details are important, only the topology. And as such, it's tempting to think about using it for topological for quantum computation. And the point is, in quantum computation, noise is a major source of trouble. Noise, decoherence are a major source of trouble. Here it seems that we have something that's not sensitive to noise. So it's tempting, and it's a line of research opened up by Alexei Kitaev. It's tempting to think about using non-abelian anyons for quantum computation. So at this point of my talk, I hope I convinced you that anyons are worth thinking about and are worth studying. But then the question is, where can we find anyons? And I'll point out two places and talk only about one. The first place is, this is a largely theoretical conference, so I should say, there are Hamiltonians you can write, you can solve exactly, exactly solvable models where excitations are anionic, abelian or non-abelian, whichever you prefer. The most famous one is called the Tori code. I guess the most famous one, it's called the Tori code by Kitaev, and the second one, and it's abelian. The second one is Kitaev's honeycomb model, and there are many others, some exactly solvable, some not. All of them have, we can either prove or give very convincing argument, have anyons as quasi-particles. But that's in theory world. In the real world, the place, the system that's most realistic where we think that happens is the quantum Hall effect. So let me now give an introduction to the quantum Hall effect. So, the first point in the quantum Hall effect is to look at the Hall effect. So I have a demonstration here. You have a two-dimensional system. You put it in a magnetic field perpendicular to the system. You push a current from left to right in my plot there. And you think about it for 2 hours, and you realize what direction the Lorentz force is going to steer this current, whether it will go to the right or to the left. After 2 hours, you'll gain a confidence, or at least I would gain a confidence level of 52%. But in any case, the Lorentz force tries to deflect the current from its motion. Therefore, there's an accumulation of opposite charges on the two sides of the sample, and there will be a voltage between the two sides. That's the Hall effect, 1860 some I think. Now, the quantity we look at is the Hall resistivity, namely the ratio of the voltage developing between the two sides to the current flowing from left to right. And since this voltage is there to cancel the Lorentz force, and since the Lorentz force is linear in magnetic field, we expect the Hall resistivity to be linear in magnetic field. And classically, once you once you cancel the Lorentz force with the Hall voltage, the rest of the the flow of the current doesn't know about the magnetic field anymore, and therefore the longitudinal resistivity, the ratio of the voltage along the current to the current, should be unchanged by the magnetic field. Quantum mechanically, the main thing before I show you the experiment, the main thing you should know is there's a dimensionless number called nu, which is a ratio of two densities. The density of flux quanta, because in quantum mechanics, magnetic field is measured in units of flux quanta. Yakir taught this to us long time ago. So it's the ratio of the density of electrons to the density of flux quanta. It's a dimensionless number. Now, and it plays as an important role in the quantum Hall effect. Anyway, now when you look at the experiment, what you see is this. What you see in green is the longitudinal voltage as a function of magnetic field. It takes a very good lawyer to argue that this does not depend on magnetic field. And in red, you see the Hall voltage, which was supposed to be linear. Now you see it's linear here. It starts linearly. It also starts independent. This is why classical theories, had some reasonable overlap with real life, at least for weak magnetic field. Also, I should say this is measured at low temperatures and so on. But anyway, you see that as you go away from the region of weak magnetic field, you see these steps, and those steps are the quantum Hall effect. What you see is the Hall resistivity stays constant, does not change. Here in this case, you change the magnetic field from 6 minus epsilon Tesla to kind of 9 plus epsilon, so a few tenths of percents, and the Hall resistivity seems not to change at all. It doesn't seem not to change at all. It doesn't change at all. It doesn't change to 1% or to 1% of a percent, or it's fixed to about 1 part to 10 to the 9, which is quite amazing. And it's quantized to units of h over e squared divided by nu, where nu, as we said before, is a dimensionless number. Now, h over e squared, surprisingly, the ratio of two of the fundamental constants of this universe, this ratio between h and e squared has the units of ohms, units that you usually associate with electrical engineers, not with trying to understand the fundamental aspects of the universe. Anyway, nu, this nu, which is supposed to be written here, fonts change as you change from computer to computer. So this nu can be an integer, in which case the effect is called the integer quantum Hall effect, or it can be a fraction, in which case the effect is called the fractional quantum Hall effect. We are going to talk about the fractional quantum Hall effect. That's the one that has anyons in it. So let me tell you in 2 minutes what you should keep in mind for the rest of this talk about the fractional quantum Hall effect. First of all, this is a solid experimental observation. This is, I don't know what's going to happen with LK99, the room temperature superconductivity, I don't know. But we're talking about something completely different here. This was measured in probably thousands of experiments over 40 years. This is there in the lab. So if you take this as an experimental observation and you add to it basic principles we know from physics, you know, the Aharonov-Bohm effect, gauge invariance, adiabatic theorem, these kind of things. Things we are not going to give up just because an interesting experiment came up. You get to three, in fact, you get to 4 conclusions, but I'll mention here only 3. You get to 3 conclusions which are unavoidable, which just come out of the experiment plus the basic principle that I mentioned. The first conclusion you must get to is that the experiment implies the existence of quasi-particles which live in the bulk of the system and carry a fractional charge. And the fractional charge is related to this nu, to this number, to the quantization level of the whole resistivity. That's the first thing. Second, and this is mostly an understanding of Laughlin. Second, that these quasi-particles, not only that they have a fractional charge, what did I do wrong? Okay. Not only that they have a fractional charge, but they satisfy fractional statistics. They are anyons. They may be abelian, they may be non-abelian, but they are anyons. And here this goes back to classical works of Halperin, of Robert Schäfer-Wilczek, and of Kivelson and Rosek. And the third is that the very existence of the fractional quantum Hall effect, number 2 and number 3 are fractional quantum Hall effect. Number 4 is the integer or the fractional. Any quantum Hall effect implies the existence of a gapped bulk and a gapless edge. And the gapless edge must carry chiral modes. What do I mean by chiral modes? That here on this, at least I'm simplifying it a little bit, but for our level it's enough, that at this edge of the system, everyone's moving to the right, and at this edge of the system, everyone's moving to the left. And the quantum Hall effect, all this beauty of the quantum Hall effect is seen because those rightists and leftists are being kept away from one another. I'll let you do the political analogies yourself, according to your taste. Most jokes in this direction were already made, not necessarily published. So anyway, those are the points you need to keep in mind about the fractional quantum Hall effect. Now, as I said, it comes out of, it's an essential, unavoidable consequence of the observation of the effect, and indeed in the first experimental paper of the fractional quantum Hall effect of Stormer, Tsui, and Gossard, they say quasi-particle with fractional electronic charge of 1/3, which is the nu in this particular case, and soon thereafter Halperin says quasi-particles at the fractional quantized Hall states obey quantization rule appropriate to particles of fractional statistics. But okay, that's fine. That's a combination of clear thinking and experimental observation of the quantum Hall effect. But we'd like to have experiments which are designed to directly measure these fractional quantum numbers, in particular fractional statistics. And today I'm going to talk only about interference. What time did I start?
So you have about 25 more minutes.
Okay, good.
Just small, the fractionalities, the 2 fractionalities of charge and statistics, they are related.
Related, completely related, yes. So here's the interferometer. Let's build it with the implicit assumption that you're going to be forgiving for my bad drawing skills. So here's an annulus, which is a fractional quantum Hall state, which has obviously, like every annulus, 2 edges, one exterior and one interior. This edge is moving counterclockwise. this edge is moving clockwise, and I can put a source here that pushes in electrons, and then I have to put a drain that will take those electrons out. We don't want to have this explode. So there will be a source here where electrons are coming in, and a drain where they are going out. Now, to see interference, we need to have we need to give the electrons possibilities, right? We need to have them. We need, at the very least, give them two drains to decide which drain they are going to get to, and then see oscillations as a function of some parameter. So that's what we're going to do now, and that will involve the internal edge. So here is, as I said, a bad drawing, mostly done on the plane. So what we do is, at 2 points, which are called point contacts, here and here, we push the walls of the sample in such a way that the two edges get very close to one another. As I said before, we see the precision of the quantum Hall effect because the two edge modes are kept away from one another. Now we make them get close to one another at 2 points. So here, tunneling can take place, and here tunneling can take place. And now you can get from here to here either by going around or by carrying out some tunneling trajectories, which we will see. That is not enough yet. We need to put in a second drain to give them a choice where to go from. Now there are two possibilities of putting that second drain. We can put it here, and that's called a Fabry-Perot interferometer, name stolen, if you want, from optics. And you see what happens. It's like the Fabry-Perot in optics. You go from the source, you get to here. Here you have a decision point. Either you tunnel and go back to this drain, or you overcome, transmit through the barrier, and then you can live in this region for a while, doing revolutions until at some point you either go out from here to this drain, or you go out from here to this drain. So what you will see as the probability of coming to this drain, it will be a sum over many trajectories. One that went straight, the other one that went one revolution in this interference loop, we will call it, or two revolutions, or three revolutions, and so on. And of course, if we work only perturbatively, then there will be only two trajectories, and most of what I'm going to talk about will be in that limit. Now, there's another possibility. We could take this drain and put it in the upper half, like this. That will be an analog to the Mach-Zehnder interferometer. Again, take the name borrowed or stolen from optics. Now there will be only two possible trajectories, because if you go like that and you come back to here, that's one possibility to get to here. Another possibility is to go like that. But any other possibility, you can look at it and convince yourself, will end up, you cannot do many revolutions as you did here, because once you face a drain, that's it, you're out of the game. You're being drained, the name implies, into the ground. Okay, so there are two interferometers. Now I'm going to talk about Fabry-Perot interferometer. Yuval here is a great expert on the Mach-Zehnder interferometer, and I think with an alert of half a minute, he can take out a talk and explain it. So if you have questions later, he can help. But I'll talk about Fabry-Perot, and here's another. This is basically a zoom in on that huge annulus that I had before. The source is here. The electrons come here and may be either reflected or transmitted. This is the interference loop, and here you go out. So there's one drain here and one drain here. This is what we call the exterior edge before. This is what we call the interior edge. And we'll work only to lowest order in this, so we will have only an incoming wave here that can either scatter in this point contact or in this point contact, and the two amplitudes sum up here, and we'll look at how we see interference there. Now, to see interference, we need to be able to change the relative phase. There are two ways to do that, either by changing the magnetic field, it's the Aharonov-Bohm effect, or by changing the area of the cell. Since the magnetic field is uniform here, if you change the area, you change the flux. And here's how you change the area. In reality, there's some gate here, and you put some voltage, and it pushes the wall, and you change the area. So you do this, and here that's data from Charlie Marcus group some years back. And you see this is the magnetic field, and this is the gate voltage, and we change the area this way. And the lines of equal phase are the line of equal flux. Flux is magnetic field times area, so it should follow in a hyperbola. And here we have only a short segment of that hyperbola, so it looks straight line more or less, but you see it's okay. So what you see here, this is magnetic field, this is area, and this is the probability to get to the second domain. And it follows exactly what you expected from the Aharonov-Bohm effect, which is if you want to stay on a constant phase, if you increase the magnetic field, you better decrease the area. So all is well, or almost well, because this is not the only result you get. You change some parameters, you change the magnetic, you go from one nu to another, you go from one material to another, you go from one details, experimental details, and what you see is this. And that's against everything we wanted, right? That as you increase the area, you should increase the magnetic field to stay at the same flux. So something doesn't conform with the usual Aharonov-Bohm effect. Now, what do you see? So the first thing you can do is let's make a poll, and maybe if we get a majority for this over this, then this wins. Or if we get a majority of this over this, the other win. Now, those of you who are not Israelis may not know, but we spend now huge amounts of our time thinking about whether democracy implies the majority rules. Democracy doesn't imply the majority rules, and physics also doesn't imply the majority rules. But anyway, let's look at what the majority says. So this is data from Heiblum Group, my colleague at Weizmann, mostly by Nissim Ofek. And those are the measurements he had, changing details which I'm not going to get to. Now, this is an amazing piece of work, and Nissim is an amazing experimentalist. Nowadays, he is one of the leaders of a quantum computing startup. But other than the experimental results, he contributed one more thing, which is he looked at it first time and said, "This looks like the pajama of my grandfather." So that gave this the name pajama plots that everyone now uses in the field. And you see there's a whole bunch of them. This looks like the non-Aharonov-Bohm. This looks like similar. This looks like a combination of vertical lines with Aharonov-Bohm lines. This looks like vertical lines, meaning you change the magnetic field and nothing changes. All kinds of them. So we need to, the original idea was to look for anyons. But those measurements are all integer quantum Hall effect, where there are no anyons. And so we need first to understand the simple case before we go for anyons. So there's a big difference between the Aharonov-Bohm 1959 paper and this realization. And the difference is Yakir and his advisor, David Bohm, had the magnetic field in a place where the electrons were not. There was a total separation, right? This was the amazing aspect. But most experiments, with maybe the exception of Tonomura, most experiments, for technical reasons, put a uniform magnetic field. It's very hard to put a magnetic field that is confined to a region of, you know, a micron or two. And in this particular case, with the quantum Hall effect, of course, you have a uniform magnetic field. So the Aharonov-Bohm phase is 2 pi times the flux divided by phi naught. And what the ideology of this, or the idea behind this experiment is we can change the magnetic field and we can change the area. And if we change the magnetic field, the area stays fixed. If we change the area, the magnetic field stays fixed. Now, you can tell that if you're an experimentalist, a professor who is an experimentalist, you can tell that to your students, but you cannot tell that to your electrons. They don't do that. In fact, what happens is as you change the magnetic field, the area changes by itself. And to understand that, we need to distinguish between two different regimes. Two different limits. The first limit is what's called the Aharonov-Bohm limit. This is a work I've done together with Izhar Neder, Bernd Rosnau, Bert Alperin, and myself some years ago. So you have to distinguish between two limits. The first limit is the Aharonov-Bohm limit, where indeed the area is changed only by the gate voltage that you apply and does not care about the magnetic field. You change the magnetic field, the area changes. And then everything is exactly as you want. You go to the fractional quantum Hall effect, you put a quasi-particle, and there will be a relative phase. There will be a quasi-particle here that will encircle the quasi-particle here, and we will measure by taking this quasi-particle in and out and in, and looking at the phase difference, we will see a phase jump that corresponds to the anionic phase. This is at least the idea, and you'll see it. It took a long time, but it's now also realized. Yes.
In the middle is the fluxon. What is the quasi-particle?
This? It's a quasi-particle with a charge, with a fractional charge.
Oh, it's a usual one.
It's a usual quasi-particle. The flux is equally spread by a big magnet, and it's uniform. So that's the 10 minutes. Thanks. This is the limit we want. And what we want is this. We want for the integer quantum Hall effect to have the flux as a function of magnetic, or the phase as a function of magnetic field go linearly up, while in the fractional quantum Hall effect, we want it to go linearly up but with a slope that's different, because you know the flux or the phase, the Aharonov-Bohm phase, has also is proportional to the charge, and if the charge goes down by a factor one third, then the slope will go down by 1/3. So we'll get regions where there will be a uniform proportionality constant between the phase and the magnetic field, and then there will be jumps, because as we change the magnetic field, there will be points at which new quasi-particles will be created, and then these phase jumps will hopefully be quantized at the right value and will be a measurement of the anionic phase. But this is only one limit. There's another limit, and this clearly is not the limit in the integer. This is not the limit that was dominant in this work that I showed you. But there's another limit, and the other limit has to do with, you sit and think about quantum mechanics and how important and beautiful it is, and then comes a very mundane consideration that the electrons decide to follow. And this is the consideration of charge neutrality. They are charged, there's a Coulomb force, and there's a second limit, which is called Coulomb dominated. Why is it called Coulomb dominated? The Aharonov-Bohm is A and B. Clearly, the second limit is dominated by Coulomb, and we needed a D. So A, B, C, D. So it's Coulomb dominated. And in this limit, as you change the magnetic field, you change also the charge density. Because those of you who remember the stories of electrons in the magnetic field, because the degeneracy of the Landau level changes, and then the field Landau levels get more and more filled. The density changes. Now, if the density changes, the electrons are alert. They need to get charge neutrality. That's the main energy that exists, and that will change the area of the interference loop in a way that you don't want. Not only that, when you put in the quasi-particle, now look what happens. When you put in the quasi-particles, the position of the edge will change. So the phase jump will not be just a phase jump of the anion phase. It will also be a phase jump for a stupid reason that, that the area changed. So this is how, this is the Aharonov-Bohm limit, and this is, even for the integer, how the Coulomb-dominated limit will go. Now, if this, so look how it goes. First of all, you increase the magnetic field, but because the area changes, you increase the magnetic field, but the flux goes down. That, for me, gave me a very old memory of my father explaining to me when I was a child that yes, his salary went up, but the taxes then went so much up that the amount of money we get, it will get smaller. So this is Israel of the socialist times. What happens here is exactly this. You increase the magnetic field, but the flux goes down. Then there's a phase jump. But in fact, what happens is sometimes, under certain, if you are deep in the Coulomb-dominated limit, this phase jump is 2 pi. And a phase jump of 2 pi you don't see. So what you will see is the flux going down with the magnetic field, which explains these lines which are 90 degrees rotated to what we expected. Anyway, what determines which of the limits you are at is a compromise between 3 factors, each dragging in its own direction. First is the quantum mechanical phase, which in the fractional case has as we said, the fractional charge comes in and the anionic phase come in, and that's our, that's what we want. But there's also the Coulomb charging energy, which is just a stupid capacitor problem. And then there's statistical physics, which tell you, this system is in some finite temperature, and it tells you how, to what extent who dominates. And if you change parameters, you can see, you can reproduce both the Aharonov-Bohm limit, the Coulomb-dominated limit, and all kinds of intermediate. So clearly, we don't want the Coulomb interaction if you want to see the anionic phase. That was a challenge addressed by all the best groups in the world for quite a few years. There were two very beautiful experiments last year. One interference, which I'm going to show to you. The other one different, collider interferometer, which I won't get into. This is really a bold decision of mine to show this plot in such a theoretical conference, but this is how the structure is built, and don't get into the details. The most important thing is you have the 2D system, and there's a metallic screen below and a metallic screen above to screen the Coulomb interaction. And what you see, this is Nakamura from Manfa's experiment in Manfa's group in Purdue. And what you see are these phase jumps, and the phase jumps are the 2 pi over 3 or close to, the 2 pi over 3 or close to it that we expect that we expect for nu equals 1/3. Now, I guess I have about 5 minutes, right? Optimistically.
Okay.
I wanted to tell you a little bit about another idea. We had Fabry-Perot, we had Mach Zehnder. There's another kind of interferometer, and I think many of you know much better than me about that. And this is the HOM, the Hongu-Mandel interferometer, in which you interfere along the time axis. In this context, it's called time domain interference, and I won't get into that. I'll just tell you that this allows us to propose two measurement techniques which are simple. You just put the voltage, measure the current, the ratio of what we get in these two measurement schemes will give us the anionic phase. So, you can ask why bother, it was already measured. This is a quantity that needs to be measured in as many possible ways as we can find, because it's a very fundamental quantity. So I skipped that, but, and I'll just say 2 words, if that's okay, about, and I'll use this. I think every one of us who are students with Yakir in Tel Aviv feel a little bit improper when we give talks on slides. We all do that, even Sandro and Lev, but that's not how we're educated. So for the non-abelian part, I'll just draw the Fabry-Perot interferometer again. And I'll tell you what's going to be different for a non-abelian state. Okay. Now, the non-abelian state that I'm going to talk about is called nu equals 5/2. And it's the simplest one to look at experimentally. It's very, very difficult. And I'm going to talk to you about interference. I won't talk to you about an amazing set of experiments carried out at Weizmann by my colleague Moti Eiblum. I'll tell you about this because it's the line of my talk, the interference. So in this state, every 2 quasi-particles have a spin 1/2 degree of freedom, or have more precisely a fermionic degree of freedom. Every 2 quasi-particles form a 2-level system. Okay? So if I have two quasi-particles here, and I go around, I should just tell you what phase do I accumulate, does a quasi-particle accumulate when it goes around these 2, and how the phase depends on whether this 2-level system is in state 0 or in state 1. So the answer is there's a pi phase difference. Okay, but that's not the crucial point, and I should be quick. So the crucial point is what happens when you have 1 here, or when you have only 1 here. And let's say the second one is here. Now these 2 have a 2-level system, kind of, degree of freedom. Now, and then what happens? If the quasi-particle, we look at the interference of this with this. If the quasi-particle goes here, it does not encircle any of these 2, and it doesn't know anything about them, and it doesn't care. So basically no interaction. But if it goes through here, in between the 2 of them, it flips the state of the 2-level system. It flips it. It acts as a measuring device. So if there's an odd number of quasi-particles here, there will be no interference, because the left one and the right one, the left one will not be measured, the right one will be measured, and the 2-level system will be able to tell. So there won't be any interference. If there's an even number, there will be interference. And that's a prediction by Alprin and myself, and by Bonderson and et al. And there is experimental support to it. It's not yet the best of all possible data, but there is some developing experimental support by Willett from Bell Labs. It's an heroic experiment. And this I have to say goes back to, I applied here much of the knowledge I acquired in the beginning of my PhD, working with Yakir and Joe Imri on the issue of how the environment defays the interference. That's what I told you. The experiment the theory is an experiment that I mentioned. And the last thing I want to do is to summarize. So what I want to say is, first of all, anyons are real. We now have experiments seeing them, and we have theoretical models. So they are part of the physics we can explore. But another point I'd like to maybe end with is, I think there's a great theoretical challenge, both theoretical and a great challenge, both theoretical and experimental, which is, at the moment, anyons live only in the quantum Hall effect and in the minds of the theorists. We need to somehow have other systems which are not quantum Hall, which we already have in our minds. We need somehow to make them real. And that's a challenge which I think is addressed and will be addressed, hopefully successfully, in the years to come. So to conclude, Yakir, thank you very much. And many great ideas and many insights that I hope we can enjoy. And thank you all for listening.
Yeah, thanks for the interesting talk. I have 3 comments. So the first one is technical. It's about the slide that starts with the experimental observation. Is the uneasy compromise?
Yes. Yeah.
Yeah, so this is only a technical question about the formula for point 3. I don't quite understand it because we have the expectation of e power I phi, and the other part also contains the same thing, I phi.
Yeah. No, phi, I should have written it better. Phi depends on the, so this is a sum of states, right? Sure. The statistical mechanics, you sum over all states. The energy depends on the state, and phi depends on the state. Okay?
Okay. Yeah. And the second comment is about the final slide of yours when you said that anyons are real. Essentially, we live in 3 dimensions. And if we reduce this degree of freedom of 1 dimension, we get effective model with quasi-particles, which are ions. So what do you mean by real? These these probabilities are only mixture of...
So okay, I'll give an answer of 2 parts. First, contrary to what we believed for a long time, there are anyons also in 3 dimensions. They are not point particles, but they are loop particles. But we can write models that have, I've done it, many other people did it. We can write models that have anyons in 3 dimensions. But second, we know how to confine systems to 2D, which where effectively the electrons live only in 2D, like take graphene, a layer of carbon. The electrons live in 2D. Can't you take them out? Of course you can. Only in low energy they live in 2 dimensions. But as long as you're confined to low energies, it's a perfectly 2-dimensional world. And we can do also 1-dimensional.
Yeah.
So,
and the third comment, which is essentially a question, is that if you really consider this surface, right, for obtaining the anyons, 2 dimensions, so I just want to have a question. Is it interesting, or have people thought about considering anions in Möbius strips?
In Möbius strips, yes. As a theoretical idea, it's nice. Realizing it means you need to change the magnet. Actually, I had once an idea. It wasn't Möbius strip, but I went to one of the greatest experimentalists of the field, Jim Eisenstein, and explained to him his idea. It had all kinds of things like that, and he said, "Come back when it's planar." So experimentally, it's out of question. Theoretically, it's an interesting question. People looked at that. I cannot say, out of the top of my head, what exactly was the conclusion, but people looked at that.
Great, thanks.
Well, two really quick questions. The same transparency with the same slide with the statistical weight. So the characteristic energy is some bulk energy, probably, presumably bulk gap energy. So the temperature should be smaller than the bulk energy in order to avoid this statistical challenge?
So this is a starting point of the negotiations. And of course, the temperature should be much smaller than the bulk gap for sure. That's not enough. Because what happens is, the system is disordered. Every system is disordered, some less, like the one of Manfred and others more. So what's going to happen is here, in the bulk, you may have a droplet of, let's say, if this is nu equals 3, this will be nu equals 4. Now, if the filling factor changes, if this number changes, there must be a gapless state. So you need to worry about the Coulomb interaction of this guy with the edge here. This is what comes into this capacitance matrix, or inverse capacitance matrix.
So the typical energy, characteristic energy,
Is Coulomb
between different areas of this inner island?
is the energy of adding an electron to this. So think about this as a quantum dot, and it's the energy of adding an electron to this.
The second quick question, I knew it, I forgot it. With these 2 nanobillion particles, you said that there is no interference, but this means that the periodicity is halved, because 2 will give you yes.
So you need to. Yeah, right. Yes, if this is not quite open, and you go to second order, then if you go twice around, you get interference. Yes.
Okay, Ellie, last question.
If there's time.
Sorry.
If there's time.
Yeah, last question. We'll do the last question.
So first, regarding yesterday, I mentioned that uncertainty is the source for all quantum phenomena. And indeed, a few years ago, Nadav Katz from the Hebrew University, he said that the spin statistics cannot be derived from uncertainty. And I found a paper by Sudrashen who proved the spin statistic theorem from algebraic considerations using convection relations similar to those leading to uncertainty. So it can be proven too. A conversation with another physicist is Eshel Ben Yaakov, the late Eshel Ben Yaakov. He was obsessed with the factor h over e squared. And he looked for a fundamental reason why this should be so, maybe a thermodynamic reason. Did you think about it? What's the profound origin of it?
Why it appears in this context, or why it appears
Resistivity or
as a resistivity quantum?
Because it has the right units.
That definitely is a good reason. Either something beyond that. Well,
He thought it should be related to entropy eventually.
yeah. I don't have a quick answer to give at the moment, but it's something worth thinking about.
May I say something?
Of course.
You have universal constants, and then any combination that gives you a certain dimension of measurable quantity should appear as a fundamental of this measurable quantity. That's, I mean, it's tautology. I mean, maybe you disagree.
No, I agree, but the question is whether there's something more, and that I don't have another argument.
Okay, let's thank Nadi.
Thank you.